Hello class. So today we're going to be talking about the first and second derivative tests. So we're taking what we learned the last few days and we're kind of all putting it into one thing. So we'll be given a function and we'll need to identify its critical points, its maximums and minimums, in the inflection points, and the intervals of concave up and intervals of concave down. So let's recall here. These three, we use the first derivative test. And then these three, we use the second derivative test. So let's go ahead and find the first and second derivatives of f of x. Excuse me. So f prime of x is going to be 3x squared plus 12x plus 12. And then f double prime of x is going to be 6x plus 12. So let's first find the critical points. So we're going to find the critical points by looking at the first derivative. So the critical points are when the first derivative equals 0. So let's go ahead and find the first derivative when it equals 0. So let me get an extra piece of paper here. I don't have much room on this one. So we're going to go ahead and use the quadratic formula on this. So remember, the quadratic formula is x equals negative b plus or minus square root of b squared minus 4ac, all divided by 2a. When we're in the form of f of x is equal to ax squared plus bx plus c. Let's see. Our a value here is going to be 3. I'm talking about the first derivative. Our b value is going to be 12, and our c value is going to be 12. So let's go ahead and find the derivatives, or not derivatives. Sorry. Let's plug it into the quadratic formula. So we have x equals negative 12 plus or minus the square root of b squared, so b 12 squared, minus 4 times a, which is 3, times c, which is 12, all over 2a, or 2 times 3. And we're going to be using, we're going to be, sorry, I'm all over the place. We're going to be simplifying this So we simplify by taking the top, or simplifying just left to right on the top, then left to right on the bottom. We've been doing the quadratic formula for a while now, haven't we? So negative 12 plus or minus 12 squared is 144. Negative 4 times 3 is negative 12. Negative 12 times 12 is negative 144. Over 2 times 3, which is 6. And we can continue going here. So x equals negative 12 plus or minus the square root of 0 over 6. And the square root of 0 is just 0. So really, we have one critical point here. And that's that x equals negative 12 over 6, or at negative 2. So our critical point here is that x equals negative 2. Now let's use Desmos to determine if it's a max or a min. Let's see, I want to try to get this nice looking for us. Okay. So here we have here's our f of x. Here's our original function. So it's a cubic, and it looks like at negative 2, it is a critical point. It is where the derivative, or where the rate of change is 0. However, it's not a max or a min, so we don't have any maximums or minimums here. So we can say in A, non-applicable, non-applicable. All right. Now let's use the second derivative to find our inflection point. So remember, the second derivative where it equals 0, that's where our inflection point is. So I can say 6x plus 12 equals 0. And let's see. Subtract 12 subtract 12, 6x equals negative 2, or sorry, negative 12, and then divide both sides by 6, and we get x equals negative 2. And that is also a critical point, right? So our inflection point is at x equals negative 2. And we saw that that is an inflection point, right? Negative 2 is right here. So before that, on the left here, this is concave down, and to the right of it, it's concave up. So intervals of concave up would be from negative 2 to infinity, and intervals of concave down would be from negative infinity to negative 2, right? To the left is concave down, and then to the right is concave up. Awesome. Let's take a look at another example here. So now we have 3x to the 5th minus 5x cubed plus 10. So again, let's take the first and second derivatives here. So we have f prime of x is going to be 15x to the 4th minus 15x squared, and that's it. And then the second derivative, f double prime of x, is equal to, let's see, that's going to be 60x cubed minus 30x. All right. So now let's find the critical points by using the first derivative. So I'm going to set this equal to 0 and solve for x. So let's see what we get. We're going to have 15x to the 4th minus 15x squared equals 0. Now, this is what I would do in this case. I would go ahead and factor out a 15x squared. Isn't it true that they both have factors of 15x squared? So yeah, let's go ahead and factor out 15x squared. So we're going to have x squared here minus 1, right? I just divided it out. 15x to the 4th divided by 15x squared is x squared. Negative 15x squared divided by 15x squared is negative 1 equals 0. Now that we have it factored, we can set each factor equal to 0 and solve for x. So we have 15x squared equals 0 and x squared minus 1 equals 0. Well, this one's pretty easy. If we divide both sides by 15, 0 divided by 15 is just 0, so we have x squared equals 0. Square root of 0 is just x equals 0. Here, we can add 1 to both sides. X squared equals 1, and then take the square root of both sides. Square root of 1 is just 1, right? 1 times 1 is 1. But it's going to be positive and negative 1. So these are our three critical points. We have one at 0, one at positive 1, and one at negative 1. So x equals negative 1, 0, and 1. Now let's use Desmos to determine which one of those are maximums, mins, or neither. Okay, so here I have it graphed in blue, and we said we had one at negative 1, 0, and positive 1, and we can see here that at negative 1 it's a max, and at positive 1 it's a min, and at 0 it looks more like an inflection point. So let's see here. We're going to have max. We have a max at x equals negative 1 and at x equals positive. Oh, I'm sorry. The one at x equals positive 1 is a min. Right? If we were to look at it, the one at negative 1 is a max. The one at positive 1 is a min. And then our inflection point. Let's use the second derivative for our inflection point. I think we already found one at 0, didn't we? So let's see here. I'm going to take our second derivative, 60x cubed minus 30x, and set it equal to 0. And here again, I would factor out an x here. In fact, we could factor out a 30x, right? 30x, and then we're essentially dividing by 30x. So 60x cubed divided by 30x, that's going to be 2x squared. Negative 30x divided by 30x is just minus 1 equals 0. And now we set both factors equal to 0 and solve for x. So we have 30x equals 0 and we have 2x squared minus 1 equals 0. So here we would divide both sides by 30. We'd just get 0, right? 0 divided by 30 is 30. Or sorry, 0 divided by 30 is 0. So x is equal to 0. And then here we'd add 1 to both sides. 2x squared equals 1. Go ahead and divide both sides by 2. So we have x squared equals 1/2. And then go ahead and take the derivative of both sides. Or sorry, not derivative, square root. I'm all over the place today. So x is equal to plus or minus square root of 1/2. Awesome. So our inflection points are at x equals negative square root of 1/2, 0, and positive square root of 1/2. Now let's check Desmos to see the intervals of concave up and concave down. So here, let's see, it looks like it's concave down from negative infinity until we get to right around here, and then it's concave up for just a little bit, if you could see that, and then it's concave down for a little bit, and then it's concave up for the rest. So if we're talking about intervals of concave up, it's concave up from negative 1 to the square root of 1/2. I'm sorry. No, it's concave up from the square root of 1/2 to 0, because our concaves happen in between our inflection points. So it's concave up from negative square root of 1/2 to 0, and then it's also concave up from the square root of 1/2 to infinity. And then intervals of concave down, let's see, it's concave down from negative infinity to that square root of negative square root of 1/2. And then it's concave down from 0 to the square root of 1/2. That just this little section, see how it's bending downward. So it's from 0 to square root of 1/2. Awesome. Now let's go to my last example here, and this is another one of our friends with e, right? So we have e times x to the e, or sorry, dyslexia there, x times e to the x. And let's see here. So let's find the first derivative. So the first derivative, we're going to have to use the product rule. So the product rule is keep the first one, derivative of the second one, plus the derivative of the first, keep the second one. So it's going to be x times e to the x, because e to the x, or the derivative of e to the x is e to the x, plus 1 square root of x, or not square root, derivative of x, times e to the x. And then let's find the second derivative. So the second derivative here is going to be, let's see, we're going to have to do the same thing to this thing again. So it's going to be x e to the x plus just 1 e to the x, and then plus 1 e to the x. And we can simplify this if you wanted to as x e to the x plus 2 e to the x. Awesome. So now let's find the critical points. And here we're just going to use, since it's e, let's just use Desmos. In fact, you could have just used Desmos for all of these if you wanted to. So let's see here. The critical point here, let's see, we have critical point here. Oh, sorry, this is the last graph. Let's see, we have a critical point right here. So this is going to be, let's see here. Critical point is going to be, let's see, at x equals negative 1. And that's, let's see if it's a min or a max. I'm going to go around it. So it goes down there, and then it goes down here. So that's going to be a max. So we have a max at x equals negative 1. Here it doesn't look like we have a minimum at all, so we're good there. And then we use the second derivative to find the inflection points. Now what I'm going to do is I'm going to go ahead and graph the second derivative. Well, in fact, I'm going to graph the first derivative too, because that's going to show us better where these inflection points and critical points are. I should have done that earlier, actually. So x e to the x, I'm graphing the first derivative here, plus e to the, I goofed, e to the x. And here we have it in purple. So where it crosses 0 is actually our critical point. So in fact we have a critical point at 0 as well. And then we should have one at -1 over here. Oh, I goofed. I didn't do plus. Sorry, this is not my day, y'all. Okay, so we didn't have the critical point at 0. My bad. We have a critical point at -1. So there we go. And so that is actually, it's not either a minimum or a maximum, is it? Oh no, it is because it's going down. Yeah. So, all right. Now let's find the inflection point. So I'm going to go ahead and graph the second derivative here. All right. So this is the second derivative here, and we can see that we have a 0 at -2, and is this a, nope, that's not a 0. So we just have a 0 at -2, so we have an inflection point at x equals -2. And the intervals of concave up, concave down, well, to the left of -2, it's negative, right? Let's see, it's a negative, yes. So that means that's where it's concave down from -infinity to -2. And then for the rest of it is concave up. So that's from -2 to infinity. And there we have it. So really, what we did, if you notice, is a little different this time. We actually solved for our critical points here when we had polynomials, right? We solved for our inflection points algebraically. You could have just as well done it graphically, like how we did it with e to the x. Now, of course, when we're working with e to the x, it's much easier to use the graph than to solve for x, right? Solving for x. So it's up to you. I just kind of wanted to show you a different way of doing it today too. You can always do it algebraically or graphically. So it's up to you. That's all I have for y'all today. So have a good day, and let me know if you have questions. Bye.